Hello, my name is Vaibhav. I'm from Department of Tripoli from Institute of Aeronautical Engineer. My topic is characteristics equations of homogeneous equations. First, introduction. This presentation explores the characteristics equations of homogeneous equations, delving into definitions, explains, and applications. Homogeneous equations first. Definitions and example. Homogeneous equations are equations where every term is a product of a constant and a variable raised to a power. A common example is the equation ax power n plus bx power of n minus 1 is equals to 0. Here all terms are proportional and can be factored accordingly. Homogeneous equation. There are several types, including linear, quadratic, and higher order homogeneous equations. Linear can be expressed in the form ax plus b is equals to 0, where quadratic may take the form ax power 2 plus bx plus c is equals to 0, where all coefficients are homogeneously proportional. Next, real world problems. Homogeneous equations are often used in engineering for structural analysis, in physics for motion equations, and in economics to model supply and demand relationship. Their structures allows for easier modeling of equilibrium situations. Next, characteristics equations. The characteristics equation arises from a differential equation derived from the coefficient of its terms. It indicates how solutions of the differential equations behave. For example, in a second order linear differential equation, the characteristic equation helps him finding the root of corresponding polynomial. Homogeneous equation. The solutions to the characteristics equations are directly related to the homogeneous equations. The roots determine the form of general solutions. Real roots lead to exponential solutions, while complex roots lead to solid solutions. Solving the characteristics equation. To solve the characteristics equation, we find the values of the variable that satisfies the polynomial equation. Sorry. Techniques include factoring the quadratic formula or using symmetric division, which provides the roots necessary for constructing the general solution of the corresponding homogeneous equation. Finding roots. Next, type of roots. Roots can be classified based on their nature. They are like real roots, complex roots, and repeated roots. Each type affects the shape of the behavior of the graph of the corresponding polynomial. Understanding these decisions is crucial in participating the system's behavior. Next, real root versus complex root. Real root are points where the polynomial touches or crosses the x-axis, while complex roots is conjugate pairs and do not intersect with x-axis. Identifying the nature of roots informs about the general behavior of the polynomial functions and its solutions. Next, multiplicity of roots. Multiplicity refers to the number of times a root occurs in a polynomial. A root, a root with even multiplicity results in a tangent at the x-axis, while odd multiplicity means the graph crosses the x-axis. This concept is crucial in understanding the graph behavior at the roots. Next, fourth, general solutions. General solutions. The general solutions of homogeneous equations can be expressed in terms of its characteristic roots. For example, if the roots are R1 and R2, the general solutions may take the form y is equals to C1 e power of R1t plus C2 e power of R2t, where C1 and C2 are continuous determined by initial conditions. Importance in differential equation. General solution plays a provide role in solving differential equation, offering a comprehensive representation of solution tutorial tailored to various initial conditions. They are essential in predicting behavior and analyzing systems across multiple science and engineering field. Techniques. Interrogating techniques such as substitutional and interrogating by parts are often utilized in deriving general solution. Mastery of these techniques allows for an essential resolution of complex differential equation, facultating the solution formation formula. Fifth one, applications. In engineering applications, homogeneous equations model states and dynamic systems. For analyzing circuits designed in the structure stability, they help they help predict failure points and optimize design across satisfy regulations, enhancing overall efficiency. Physics applications. Homogeneous equations guide various physical models, including homogeneous function and wave functions. They assist in formulating laws of motion and energy conservation, reflecting real-world phenomena through mathematical expression. Economical applications. Economical applications. In economics, homogeneous equations helps in modeling consumer behavior, supply demand curves, and making equilibrium. The They provide insight into optimizing resource and managing risk while considering multiple economic factors. Conclusion. In summary, understanding the characteristics equations and its relationship with homogeneous equation is essential across various disciplines. This knowledge facilities better provide solving techniques for its practical applications in real world scenarios. Thank you.